Hello everyone and welcome to my thesis presentation, which is titled Video Coding Enhancements for HTTP Data Streaming Using Machine Learning. And this will be the agenda we will be following for today. We will start with the introduction, and then we will cover 2 chapters from the thesis, and then we will finish the presentation with the conclusion. Without further ado, let's jump into the introduction. First of all, I would like to start with why do we even need video coding enhancements in the first place. And the first reason is we see the user's expectations are increasing. Like if you think of it, when you think of the previous 10 years ago, it was okay to wait 10-20 seconds to start watching a video, but nowadays if you even wait for a couple of seconds, we assume something is going on wrong. And on the other hand, the quality of the video content is getting better and better. And nowadays, everything, even the shortest videos we see are getting a professional grade production level, and that also increases data size and the display quality and the video quality as well. And on the other hand, the demand for the video is getting increasing. Like 10 years ago, when you think of a group chat, it was something text-based, but nowadays we use video for the group chat. And that is not just for the group chat, the video is getting more and more common and becoming the primary tool for communication in our today's world. In terms of machine learning, we also see the tools that we are using are getting better and better and smarter. Like the assistant concept is totally changing. Now we are trying to integrate machine learning in the daily aspects of our lives to make everything a bit more smarter. So all these topics, like we know that the expectation from the users are increasing, and the quality of the video content and also the display technologies are getting better and better. And on the other hand, we also have an increasing demand for the video. That means that all these things combined, we have an increasing demand for the video coding, and that requires the need for improvement in the video coding. Speaking of video coding, we also see the codecs getting better. I mean, these numbers are also supporting us. And like we see that it's almost 6% of the entire sharing the internet traffic is the video content in the recent reports. And also we see a shift towards a higher resolution content in the recently. Of course, these are also supported by the video codecs. Like we can start with the 2003, which was the release of the AVC, the standardized video codec, which brought the support for 4K support and then provided enough support for the contents need in that time. Then 10 years later, we had the HEVC release, which increased the supported content resolution with the introduction of new and more complex video encoding tools. And recently in 2020, we saw the release and standardization of the VVC, which brought the support for even higher resolution and different content types. But also, all these changes comes with a cost, and that is the increasing video coding complexity. Like from AVC to HEVC, we saw the 37% around bitrate saving on average, but that came with the cost of almost 2 times encoding time complexity. From HVC to HVVC, the story was totally different. I mean, again, we managed to save around 35% bitrate saving on average. But this time, the encoding time complexity increased almost 10 times. So we see the increasing content complexity is becoming an issue in the future, and then that is something that needs to be tackled. Speaking of the codecs, we would like to go over the video coding pipeline. So we start with the source video, and then in the encoding steps, we apply these operations, and then at the end, we get the encoded video, which is ready to be streamed over the internet. Then on the decoder side, we more or less apply the inverse of these operations, and at the end we get a decoded video that is ready to be displayed to the user. I should note that this in-loop filtering step can also be applied to between the motion compensation to better improve the accuracy, but for the sake of simplicity, I illustrated like this for now. And then the question was like, okay, we know this is the pipeline we have. So how can we utilize machine learning in this pipeline so that we can either improve the performance of the individual components, or we can improve everything overall? And then the thinking process brought us these opening rules. For example, some examples here. For example, we can start with the partitioning prediction for the block partitioning step. We can utilize this machine learning here to improve the performance a bit more, to speed up the process. Or we can utilize machine learning at the end so that we can apply super resolution with the machine learning, and then we can get a better visual quality for the end user. Once we had these results, we had to come up with some research questions to be tackled during the scope of the thesis, and then we came up with 4 research questions. The first one was about how to efficiently provide multi-bit representations over a wide range of resolutions for HTTP data streaming. This is an important problem because in HAS we need to prepare the same video in different resolutions and qualities so that the users can select the ones that is most suitable for the network conditions. But that means that we need to do a lot of encodings for the same content. So we need to find a way to speed up this process. The second question was focusing on how can we improve the performance of the video codec using machine learning. We saw in the pipeline that there are some components that we can utilize machine learning to boost their performance. So the question is how further we can progress the video codecs using machine learning. Third question, we shifted the focus a bit more to the visual aspect, and then we tried to improve the visual quality of the videos using machine learning. So for example, we could utilize super resolution at the end, as we saw in the previous slide, that to boost the visual quality of the decoded video so that the users can have a better and more pleasant experience. And finally, how can we utilize the machine learning to improve the perceptual quality assessment of the videos? I mean, we can do all kinds of improvements, but as long as we don't have a certain metric that is robust and capture the needs of the users, all these measurements cannot be validated that they provide a better experience for the users. And these research questions actually result in 8 total contributions in the thesis. The first publication, we focused on improving the multi-bitrate performance with the machine learning. And then in the second publication, we extended this solution to cover the multi-resolution scenarios. Then in the third publication, I changed the focus a bit more to study codec components individually, to dive deeper in this video coding pipeline and then find the more rooms where can we utilize machine learning. Then I shifted the focus towards a bit more research question 3. There, the first publication was about how can we improve the visual quality of the videos in the context of HAS with the machine learning. And this was a result with a publication that covered the ABR that can cover super resolution approaches on the go. Then the fifth publication, during this, I found out that there is a lack of evaluation platform for the machine learning based improvements for the mobile super resolution, especially for in the context of HAS. So I proposed a platform to evaluate the machine learning based quality enhancements on the mobile devices. And then in the sixth publication, during the studies of P4 and P5, I found that the existing super resolution networks are focusing on the powerful hardware components, which is not the case for the mobile devices. So I've tried to provide a solution that can work on the mobile device limitation while also provide a state-of-the-art quality in terms of the super resolution. Then final 2 publications were a bit more exploratory. In the 7th publication, I dived into the light field image coding, which is an immersive media file, and I wanted to utilize super resolution to improve the coding efficiency in that aspect. And then finally, I wanted to improve the perceptual quality assessment using the machine learning. That was a study that was done with the recently released vision transformers, and then I wanted to explore how good they are in terms of assessing the performance. And in this presentation, I will be covering only half of them due to time constraints. So we will be covering the presentation, publication 1 and 2, and also 4 and 6 in terms of research questions. And this is the list of the publications I had during the context of the thesis, scope of the thesis. So let's jump into the fast multi-rate encoding, which is the first chapter of contributions. So here, as I mentioned before, in HAS, we need to prepare the same content in different resolutions and quality levels. So typically in a HAS encoding scheme, we have this type of representation for a single video. We have 3 different resolutions, and each resolution we either have 2 or 3 quality levels, but these numbers can also increase and decrease based on the use case. But the main problem is all of these content are actually the same. This is the same source video we have, but we just need to prepare in different resolutions and quality by changing the metadata, but eventually we are working on the same content. So that means we have the same content, but we need to provide different outputs. That is actually causing high redundancy, and that is something we can exploit to improve the performance, especially in terms of the time complexity, to provide a more efficient solution here. And that was the goal of this chapter. And this, we jumped into the literature to see how it was done before, and then we saw the most common approach is the selecting a reference representation. So this means we select the reference representation, which is usually the highest or the lowest quality representation we have, and then we encode it. And during the encoding, we save the encoding information, like the block structure and reference rhymes or other available information. And then during the encoding of the remaining representations, which are name dependent in this case, We use this saved information to speed up the encoding process. I also saw two main problems here. The first one, most of the proposed approaches are not improving the parallel encoding performance. So, for example, if the approach selects the highest quality as a reference, then before starting the other dependent representation encodings, we need to wait for this to be completed first. And that means all this time is actually a bottleneck for us because we cannot start this encoding of this before this is completed. So if we were to run all of these in parallel, we have this bottleneck scenario. That is something we need to focus and we need to solve. The other part I saw in the literature is almost all the methods agree that the block partitioning steps takes too long, and that is the main area they try to tackle with the multi-rate encoding. Because, when you think of this example in the HEVC context, it first takes the frame and then divides into small blocks based on the motion and the texture complexity. By default, HEVC uses 64 by 64 block sizes as the default partitioning, but it can go deeper and deeper and deeper based on the complexity of the block. So, the problem here with the HEVC, it does this in a brute force manner. So if you want to find the optimal partitioning scheme for a single block, you need to try out more than 83,000 possibilities. And if you think of it, there are more than 510 blocks in a 1080p frame, and you have typically 30 frames per second. And if you make the calculation for like 10 minutes of video, this is too many calculations in the brute force manner, and that of course takes too much time to encode. So I saw these two problems, and then we had to tackle these in a way that we solve the block partitioning complexity and also improve the parallel encoding. And I propose two methods here. The first one is named FameML, which is a multi-rate encoding scheme that uses some convolutional neural network to guide depth decisions. And I had to focus on parallel encoding, as I said before, due to focus on this bottleneck problem. And then in the second publication, I extended this approach to cover the multi-resolution scenarios. That means I had to extend the convolutional neural network structure and add more features and in-depth evaluation here. So we start with the first publication, FameML Fast Multi-Rate Encoding, and which is published in the 2020 VCIP conference. Here, how it works. It is a CNN guided solution that utilizes reference encoding information to speed up the dependent representation encodings. And we focus on improving parallel encoding here. So we have the input video. Normally, this is the typical Haas encoding scheme. So if we were to do it normally, we just encode all of them individually, independently from each other. And if we take the single resolution but different qualities, this is we name multi-rate encoding. But if we include all of them, this is the multi-resolution encoding. But for the first publication, we focus on the multi-rate part. So we are considering the same resolution but in different quality levels. And this is how it works. We first start. We know that we have a certain number of quality levels we need to encode with. We start with the encoding them lower quality representations because we try to focus on the parallel encoding, which means that bringing down the encoding time complexity of the high resolution and high quality representations. And then we try to find out which is the optimal selection of the reverse representation. And we found that selecting the middle quality representation works best in terms of the trade-off between the visual quality and encoding time complexity. So we select the middle quality as a reference representation, and during the encoding of it, we save the encoding information. Then the encoding information of the reference is used to encode higher quality representations by the guidance of its convolutional neural network we include here. And this is the structure of the convolutional network we use. We first process the YUV channels separately, but since the Y channels include more information, we separate them with an additional layer. Then we concatenate them together, and then we process them using the 4 different convolution blocks. And then we pass it through the fully connected layer to get the softmax decision at the end. This is the decision of should we split this block further or not. And then we want to also include the encoding information we saved from the reference, and then here we add this feature vector that's extracted from the reference representation, and then pass this again with another set of fully connected layers, and at the end we get the decision of should we split this block further or not. Feature vector we use is actually, as it was shown before, is a 14 valued vector. The 5 values are coming from the RD cost, which is the counting of bitrate cost of encoding the reference block. Then also the variance of pixels in the reference block, average motion vector size, the step level selected in the reference block, the frame level QP for the current block, and the PU decision given in the reference block. And the second publication was an extension of the first one that's trying to cover the multi-resolution scenario, which was published in the IEEE Open Journal of Signal Processing. So here we improved the convolutional network architecture and we utilize more features. We also extend the feature set, and we also target both parallel and serial encoding in this study because we have too many representations to encode it. And this is how it works. We start with the reference representation selection, which is the highest quality representation from the robust resolution. Again, this was finalized by the trial and error process, and this was giving us the optimal trade-off. And then once this is encoded, we save the encoding information, and we utilize that encoding information to speed up the encoding of all remaining representations. And we start with the results from the FameML first, which is the first publication. Here we can see the normalized encoding time graph if we were to use the reference HEVC software. And then we compare with the lower band approach, and as again selecting the middle cut as the representation. Lower band here means, assume we select the depth level 1 here, so that means that there is no need to search for depth level 0 here, because if you go higher in the quality level, you go deeper in the depth levels. And once we do that, we can see we can actually decrease the encoding time complexity, but it was not that significant. But when we boost it with the help of the convolutional neural network, we can see we save around almost half of the encoding time from the highest quality representation. And at the end, we get the more or less balanced encoding time complexity distribution, which means that we don't have an obvious bottleneck in terms of the parallel encoding. In the first ML, the scenario is the same. We compare with the reference HEVC software and the lower bound approach. Then we may apply this convolutional network. Again, we see a quite significant drop in the encoding time complexities for almost all resolutions, representations. And here also the BD rate performance of the first ML is given. Here you can see it can save around 50% encoding time, but the cost of the BD beyond delta rate is around 3% for the 4K, and on average it's around 2% for the PSN and 2.3% for the VMAF. So we managed to save quite a lot of encoding time complexity while also not increasing the bitrate too much. So that's actually quite significant an achievement for us. So in this chapter, I presented two publications. The FameML was a fast multi-rate encoding scheme guided by a CNN, which manages around 49% speed up in parallel encoding. FirestML extends the scenario to fast multi-resolution scenarios, which manages to save around 47% in overall encoding time, but with just only 2% beyond the delta rate increase. Let's jump into the second chapter of the thesis, mobile super resolution. So the reason why we wanted to work with mobile devices here is that almost 70% of the YouTube watch time is coming from mobile devices. But on the other hand, it is reported that 1/4 of smartphone users encounter video streaming problems every day. So there is a huge demand, but there is also a problem that with the streaming, so we need to find a way to solve this. And when we see also the machine learning execution power of mobile devices, I saw that they are getting quite powerful in the recent years. Like in the span of 3 years, the execution power almost tenfolded. So that indicates in the upcoming years we will have real powerful mobile devices in our pockets, but that power is not well utilized. So there should be a solution that utilizes this power to solve the existing problems in the video streaming pipeline. But we cannot just take the existing neural networks from the domain and then directly apply them to mobile parts, because they are not designed for the more power limited scenarios. So if we were to make an analogy, let's say we want to go for a camping and we have a really powerful car with us, that means we can carry all the high-end and very heavy utility devices with us to the camping. But if we make the analogy our car becomes a very, very small one if in the mobile devices. That means we cannot carry all of these, but we still want to utilize these tools and then have fun in the camping. So we need to find a way to sacrifice and then bring the smaller versions with us, but still enjoy the camping with us. So that is the challenge we need to tackle here with the mobile device limitations. So the existing super resolution networks are designed for powerful hardware, which we don't have with the mobile devices yet. Maybe it will come in the future. But also the mobile solutions for the HTTP data streaming are quite limited. So I saw these two gaps and that wanted to tackle with the problems here in my thesis. And then that I propose two methods here in the context. The first one is the SR-ABR, which is an ABR algorithm that considers the super resolution application on device, which also proposes the lightweight super resolution network that can be executed on mobile devices. But then I also proposed the LiDAR because the execution performance of the SR-ABR network was quite not that well. And then I tried to design a lightweight super resolution network that considers the limitations of mobile devices that can execute real-time video processing on mobile devices in all cases. Super resolution based ABR, the SR-ABR was published in 2022 in ACM One High Video Conference, and we start with that. So here how it works. We get our client. We first send the device information to our streaming server, and the server we store set of super resolution networks in different qualities. And based on the device information we get, we select the suitable set of networks and send it to the client and store it there. And we do it only once before the initial setup. And during the playback phase, again, the ABR algorithm gets the device information and all the other ABR related algorithm information like the buffer and the network level. And then ABR can have three choices. It can directly request a high resolution segment if the network conditions are fine and then directly displays it. Or if the network conditions are not good, it can request a low resolution segment and directly displays it. Or before displaying the low resolution segment, it can actually apply the super resolution and display the higher visual quality version of the low resolution segment. So this is the part that we introduce here in the SR-ABR. So that changes the balances a bit because normally, let's say we have three resolutions available and then the throughput cost for them will be like this, which is similar to buffer cost, and the quality cost will be like this. So in this scenario, ABR can choose the middle quality because that has the lowest average quality cost. But when SR comes into the play, this scenario can change because we can actually improve the quality of this segment quite a lot, so that the quality cost will be lower than the middle quality. Then if we have the SR in the equation, then the ABR should choose this resolution. So this is the novelty of the ABR we introduced. It considers the super resolution aspect in terms of the streaming. And the second approach is LiDAR, which is published in 2022 in IBM SB conference. It is a very lightweight super resolution network that considers the mobile device limitations. And this is how it works. It takes the group of low resolution frames and it processes them using two dense resolution blocks, which I'll explain soon. And then pass through the convolution layer, which applies the clipped ReLU activation because this clipped ReLU works better in the quantized version of the network, so we don't lose that much information. And then I apply the pixel shuffle layer at the end to get the high resolution group frames. So dense resolution block is structured like this. It applies two set of convolution and ReLU operations consecutively. And then before applying the third one, it adds the output from the first layer to the output of the second layer. And this addition structure is repeated throughout the net blocks. So we have very dense connections here that enables us to process more information using fewer number of layers compared to the traditional ones. And the SR-ABR in the network we used in the SR-ABR can still manage 24 FPS for the 2x upscaling, which is not the case for the state-of-the-art networks. And also it can manage quite competitive performance with the SOTA networks. But the key point here, both of them performs much better than the bilinear upscaling, which is the default upscaling method used in Android. So if we use any of them, we still get a quite well improvement for the visual experience. And in terms of the ABR performance, we can see that SR-ABR gets quite saving in the average bitrate consumption, while also managing to get the highest quality of experience score. And also we include this VMAF over bitrate score, which is like indicates how much of the quality we can extract per delivered data, which demonstrates the efficiency of the ABR algorithms. And here ABR also takes the lead. And the LiDAR results is like this. When we check the execution speed, LiDAR can perform quite fast in the mobile devices, and like it can still stay above the 60 frames per second even for 2 times upscaling. And in terms of the objective quality results, again, it is compatible with the state-of-the-art neural networks, but the key point is it's still much higher than the bilinear upscaling. So if you use this, you can see quite well improvement in terms of visual aspect, and you don't lose much quality compared to state-of-the-art, very heavy super resolution networks. So in this chapter, I propose 2 publications. SRIBR is an ABR algorithm that leverages super resolution to improve the visual quality. It can manage up to 44% bandwidth reduction while providing 15% higher quality of experience. And LiDAR is a neural network for mobile video super resolution that can be executed on real time in almost all scenarios. And to conclude my presentation, I will go over the 4 publications I presented today. FameML is a fast multi-decoding scheme guided by a CNN, and the FireSML is an extension of it to the multi-resolution scenarios. Then in terms of the mobile video super resolution, I proposed an SRABR, which is an ABR algorithm that leverages SR to improve quality, and then LiDAR, a lightweight neural network for mobile video super resolution. And in terms of the results, FameML manages around 49% speed up, Fares manages around 47% speed up, and then SRABR can reduce the bandwidth around 44% while providing higher quality of experience. And finally, LiDAR can be executed on real time on mobile devices. And that concludes my presentation for today. I hope you enjoyed it, and if you have any questions, you can reach me via email or any other channels you find. Thank you very much for listening.